is the one I wanted, sorry. Okay? So, we've been talking about differentials and change and moments, but now we're ready to start one of these two endeavors, and that is endeavor B, okay? So we're ready to begin with this endeavor in the next few weeks, about 3 weeks. You know how fast something is changing, and you want to know how much of it you have. So how is it mathematically or in a context that we would know how fast something is changing? What would we have? What would we have where we could say, oh, this is telling us how fast a quantity is changing? Okay, yeah, so we would have rate of change. So in what form? In what form would we have rate of change? Okay? Or at lots of moments. And what would that be? If we had rate of change at lots of moments, that would be called a... So we have the rate of change at this moment, and the rate of change at this moment, and then this moment, and then this moment. What would that be called? I haven't heard it yet. I've got the rate of change at this moment, and then, or I've got anything at this moment, and then this moment, and then this moment, and then this moment. What is that the idea of? A function. Did someone say that? A function. A function gives values of a dependent quantity given values of an independent quantity. Okay. Can you read that in the back? I'll read it to you. Function RV gives the rate of change of volume of oil expelled per day by a rig that begins leaking at t equals 0 days. So the function we have is R sub V. R sub V, and that gives the rate of change of volume of oil expelled per day by a rig that begins leaking at t equals 0 days. And here is that function, a visual, a display graph of that function. Okay, so first of all, can you imagine a function v then that gives the total amount expelled x days after the rig started to leak? So what is this? This is a rate of change function telling us at any moment since the oil started to leak what the rate of change is. So can you imagine that there would be some function that would tell us how much total oil has expelled x days after the rig started to leak? Can you imagine that? Yes. Not what it is, but that there would exist such a function. Okay? All right, well, here's what that looks like. So now this function then is showing the total volume of oil having leaked after x days. Okay? All right, and so then this is our idea is that you know how fast something is changing, right? Rate of change function is given. And you want to know how much of it you have. Total quantity function. Okay? So, but we're just imagining that, and we don't have that in our context. We just imagine that it exists, and we're kind of going to put the building blocks in place in order to develop or create such a function, the quantity function. Okay, so our endeavor over the next few weeks will be to develop a quantity function like v, given its rate of change function r of v. Or R sub V. Okay? So we imagine it, but we don't have it. We have the rate of change function only. That's where we're starting, okay? So I have a couple questions for you to talk about. And first is, how does the statement R sub V of 0.7 equal 9.68 relate to the graph of R sub V? And what does R sub V of 0.7 equals 9.68 mean in this context? So this will take a couple minutes. So how does this statement right here, how does it relate to the graph? And then what does that statement mean in the context? Did you learn anything from your readings? Go! Meters cubed per day. And so what about the graph? So how does that relate to the graph? So you're kind of answering more the second question, which is good. But how does that relate to the graph? Oh, is there... What's that? It shows the rate of change. Okay, yeah, yeah. Yeah, right. So watch. Ready? At 0.7, the rate of change is 9.68, and that's a correspondence point on this graph. Okay, that's a correspondence point. 0.7 and 9.68 is one of the points you're looking at when you look at that red curve. Okay, and so then what does it mean in this context? So from the reading, so did you learn what does a value of the dependent variable or a value of the rate of change from a rate of change function mean? What does it mean? Yeah.
After 0.7 days, the oil rig is leaking 9.68 meters cubed.
Okay. He said, and this is what he said as well. After 0.7 days, the oil rig is leaking at 9.68 meters cubed per day. Okay, that's true, but there's something missing there that we want to emphasize. Does anybody remember from the reading? Yes, sir.
Are you thinking like around that moment?
Okay.
So in a small interval that includes 0.7.
Okay.
The function has a constant rate of change of 9.68.
There, he nailed it. He said at the moment 0.7, in a small interval around 0.7, that the rig is leaking at essentially a constant rate of 9.68 at that moment. Okay? So at the moment, 0.7 days, the oil leak at essentially a constant rate of 9.68 meters cubed per day. This is crucial. All right? This is really crucial that this is how you're interpreting the values of the dependent variable when you have a rate of change function. Values of the dependent variable, or the y values, right? Meters cubed per day. That at that moment, 0.7, it's saying that whatever the value of that dependent variable is essentially a constant rate for that very small interval, or that moment at 0.7. Okay, remember that from the reading? Okay, so here I'm showing then a zoomed-in version here with different scale. And I'm, so how am I, okay, so let you give it a chance to talk. How am I representing what we just said with this new graph? Okay, talk. How am I representing what we just said with this new graph? Go. Okay, so we're winding down here. So, somebody new. How is this graph showing what we just talked about the meaning of the dependent variable for a rate of change graph? Yes, sir.
Okay, so this is, the blue is in respect of 9.68, but as it's going down, you see 0.07 is in respect of 0.7 to 7.3. We're kind of looking at the moment in which the change is happening.
Okay.
Linear rate.
Okay. So what's the red? What's being shown by red, and what's being shown by the blue segment? What's being shown by the red, and what's being shown by the blue segment? Yes, sir.
The red line is the actual function
Okay.
line. The blue line is 9.68. It's the y equals 9.68. The tangential line represents that small rate of change.
Okay. Pretty good. So the red is the actual rate function, and the blue line. So it's not a tangential, but what is that blue segment representing? Yeah.
It's describing the value at that moment.
Okay.
The blue line is linear. It's describing at this point, this is the value we're seeing.
Okay.
And that is effectively at 0.7 there, you will see that it has a value of 9.68.
What has a value? What?
The rate of change.
The rate of change. Oops. Okay. Right. So yeah, the blue segment then is showing. We said what? It's essentially a constant rate. So a constant rate is going to show up how in a rate of change graph. A constant rate will show up how in a rate of change graph. But there's not just linear. Okay, so here, watch this is all linear. Like this is linear, this is linear, this is linear. So how will a constant rate of change show up in a rate of change graph necessarily? It has to be horizontal, right? It has to be horizontal, meaning as x changes, the rate doesn't change. It stays at that value. So that blue segment is showing that at the moment 0.7, we have essentially a constant rate. So that all through this interval here from 0.7 to 0.702, we're taking the rate of change to be constant at 9.68. Okay? So in a rate of change graph, constant rate of change means a horizontal line, not just any line, right? Not just any line. It's got to be a horizontal line so that you're saying for a little change in the x variable, the rate doesn't change. It doesn't go up or down. The rate stays constant. So this blue segment is showing essentially our constant rate. Okay, the blue segment. Okay, so suppose that for argument here that the V of 0.7 is 13.18 meters cubed. So this is our quantity function now. We're saying after 0.7 days, the total amount of oil that's been expelled is 13.18 meters cubed. And so we've got a correspondence point for that. So 0.7, 13.18. Is that here? I think that's here. Yep. Okay, so that's this now. This is a different function, right? This is the quantity function. This is the total amount of oil that's leaked after 0.7 days and up to 0.7 days, and that's 13.18 meters cubed. And it's a lot easier to see up here. Yeah. Okay, I got it. No, I didn't. I'm too high. These are by ones. I need to do it this way. I need to look on there. Right there? Thanks. It's really hard on my screen. It's too small. Okay, now I got it. Okay, so under our assumptions, what is V of 0.713 days? And then in that case, what is dx and dv? What is V of 0.702? And what is dx and dv? So we have to apply what we've been learning in the last couple of weeks here to understand this and do this. So, and this is the idea of building the amount function out of the rate function. So this would give us, if we can find V of 0.713, we just got one correspondence point of that amount function. And if we can find V of 0.702, we just got another point. And so it's like we're building the function that gives us total amount, knowing the function that gives us rate of change. Okay? So this is where we're applying what we've been doing the last couple of weeks and what you did in the reading. See if you can put this together here. So what is V of 0.713? What are dx and dv? What's V of 0.702? What's dx and dv? And we need to know how to do this. So if you're struggling, get help. Okay, get help. Okay, the TAs will be walking around. You've got people around you. But this is a crucial skill that we should have by now. Okay, ready, go. Right? Do you get it? I will make little mistakes like this, but that has a great impact on the work you're doing. Yeah, right. So here I'm showing this constant rate, only up to 0.702. So it doesn't make sense to use that constant rate at 0.71. Why not? At 0.713. Why doesn't it make sense? Yeah, by then, so this constant rate really won't apply anymore because the rate will be lower. Will be much lower than that by then. So we're only assuming it's essentially 0.968 for a small interval around 0.7. Okay, so do you want to work on it again? Okay. So anyway, so I'll do this and then you can go back and look at 0.702. So for 0.7013, so first of all, so really the first question we ask is what is dt? What is dt for 0.7013? Change in time, which is what? We're changing from 0.7 to 0.7013, so that would be 0.0013. And we can represent that like this. That's our little change in time. Is that about to the right place? Go further. Okay, and then what do we need? So we want to know what the final volume is, so we need to get the change in volume over this time. How are we going to get the change in volume over this time? This rate of change is, this constant rate of change is telling us how many meter cubes per day, and we have this many days, right? This many days is going by, and our constant rate, we have essentially constant rate at 9.68. Right, so it's going to be our m dt, right? M, constant rate of change. We worked hard on it because we're going to use it a lot. 9.68 times dt, 0.0. Put that there. I just needed 9.68 times. Okay? And does anybody have that? What's that? 0. And what are the units on that? What did we just calculate? 0.125 what? Meters cubed, additional meters cubed in that little amount of time according to a constant rate of 9.68 meters cubed per day. So then if that's the case, if we increased our volume by this much, how do we find the new volume? You've got this much additional volume plus that. This is the idea that V of, this is 0.7 plus dt is essentially equal to, so this would be the actual volume, okay? So this would be the true volume, but we're using this little constant rate to find a volume that's essentially the same as that, but would be slightly different, okay? So it would be our V of 0.7 plus what? Just in symbols, dV. And that dV we found by m dt. Super important principle here, that this volume at 0.7013 is essentially the same as our volume at 0.7, plus the little change we get by assuming that the rate essentially stayed constant for that short amount of time, that 9.68. Anyone got a value? So that we want the dV is going to be the 0.0125 plus 13.18. So is it 1925? 1925. So it's going to be just above this line right there. Right there. So we have a new correspondence point of volume. And that new correspondence point is 0.7013 and 13.1925. And that came from the old V plus the change in V. And the change in V we got from m dt. So this gives us that new point. And if all the way from, if between those, if in the time frame from 0.7 to 0.7013, we're assuming an essentially constant rate, then what about in between? What about the volume in between those two? How did it increase? Linearly, right? So it went up linearly. So that the constant rate of change, that quantity is increasing at a constant rate of change, so that would be a line. Okay, anybody have a question on this? Does it make sense? Okay, so do you want to work out those who maybe didn't exactly do this or are understanding it better now? So let's go ahead and take a couple minutes, work out V of 0.702. Okay, work out V of 0.702. Go. Okay, what's dt? 0.002. I'm going to do this second example in blue, okay? So dt is now out to here. So now the dt for the blue one is 0.002. How do you calculate the corresponding dV?
You want to take 0.002
mdt, right? Because if it's changing at 9.68 meters cubed per day and 0.002 days just went by to get the meters cubed in 0.002 days, you're just going to do mdt. So 9.68 times 0.002. Who's got a result for that? 0.19. How about one more decimal place? 4. How'd I do? Is that right? Okay, so now we've got over those 0.002 days, we have, according to a constant rate of change at that moment of 0.7, we have an increase in volume of 0.0194. So to get the new volume, we would do same thing we did before, right there. You're going to take the 13.18, which is the volume at 0.7 days, and add that little change. And you get 13.1994. So almost to the line. So here's our new DV. And our new point is 0.702, comma, 13.18 or 1994. Okay, anybody have a question? Is this starting to make more sense now? So the idea is that for this moment, we're starting for this moment, we're building the volume function. You see? So in fact, we really know every single point in there because we know this is a linear function. Given any time close to 0.7, we could go through this process and get the corresponding volume. Okay? So this is really building the little teeny, it's building a moment of the volume function. It's building the moment around 0.7 of the volume function. And here's two examples of values of volume in this vicinity of 0.7 days gone by. So again, the idea that you know how fast something is changing and you want to know how much of it you have. We just did one little moment of that. One little moment of that. We know that it will increase linearly according to 9.68, a constant, essentially constant rate of 9.68 meters cubed per day. Okay, questions? Okay, 2 minutes to talk, and then you get a top hat question. Go. So what was the big takeaway today? Go. Okay, get ready. Top hat. Okay. Talking stops now. Here we go. 2 questions. 1 answer. Only 1 answer for each, okay? Just 1 correct choice for each. No talking.